So if you want to know if a new biotherapy is safe for human vaginal tissue, you don't actually test it on a human,
No, definitely not right out of the gate.
right? And you don't test it on a lab rat either. You test it on like a 9-day-old unhatched chicken egg.
Yeah, or sometimes a microscopic layer of human cells that are, fed by a liquid under a fake plastic sky.
Exactly. It sounds like science fiction. But welcome to the deep dive. Whether you're prepping for a medical meeting, catching up on biotech, or you're just, insanely curious about how things work behind the scenes, we're so glad you're here.
It is a really fascinating stack of sources today. We're looking at a very unique intersection of advanced biotechnology research, clinical evaluations, and cosmetic gynecology.
Yeah, and our mission today is to uncover the rigorous hidden laboratory science of intimate polynucleotide formulation.
Which is a mouthful, I know.
It really is. But basically, we want to know what exact laboratory parameters scientists use to measure if these DNA-derived therapies are biocompatible, and how do they actually prove these products stimulate cell viability before they ever touch a patient.
Right. And to set the stage for you, we should probably define what we're actually testing here. When we talk about polynucleotides or PNs,
And polydeoxyribonucleotides, PDRNs, right?
exactly, PDRNs, we are talking about highly purified DNA fragments.
And just to be clear, these aren't full genetic codes. The literature notes they are typically, 50 to 2,000 base pairs long?
Correct. They are short, fragmented strands. And in the medical aesthetics and intimate health space, they are most often extracted from, well, the gonads of trout or salmon.
Which sounds incredibly strange when you say it out loud.
It does, but fish DNA in this specific fragmented form is incredibly compatible with human biology. That is, of course, once it's rigorously purified to remove any proteins that could trigger an allergic reaction.
Right, so in the context of intimate health, they're essentially acting as biostimulators. Their job isn't to introduce new genetics.
No, not at all. Their job is to improve tissue hydration and stimulate fibroblast activity in the vaginal mucosa.
So they're basically signaling the tissue to repair itself, but doing it all without hormones.
That's the clinical goal. But getting to that clinical goal requires a product to prove itself in the lab first. You can't just, mix up some purified fish DNA in a tube and hope it regenerates human tissue.
Yeah, that would be a bad idea. Which brings us to the very first hurdle. If you have this new formulation, you need to prove that human vaginal cells actually survive and thrive when exposed to it.
The viability gauntlet.
Exactly. And if you're listening to this and wondering how scientists can possibly see, invisible cell metabolism to know if a microscopic cell is happy, it turns out it comes down to a color change.
Yeah, a very specific color change. That is the foundation of the cell viability assay. And the gold standard for measuring this in the lab is the MTT assay.
And MTT stands for, let me check my notes, a highly complex tetrazolium bromide compound.
Yeah, thankfully the industry just calls it MTT.
A rare moment of mercy from the chemists, honestly. So how does this dye actually measure life?
Well, it measures the metabolic activity of the cells. You introduce this yellow MTT dye into a culture of cells.
Okay, yellow dye.
Right. And if the cells are viable, meaning their metabolisms are actively running, they're breathing, they're consuming energy-specific enzymes inside those cells, we'll convert that yellow dye into an insoluble purple product.
And that purple product is called formazan, right?
Exactly, formazan.
So if the cells are dead or dying because the formulation is toxic, the dish just stays yellow. But if they're healthy and active, the dish turns purple. And the healthier the cells, the darker the purple.
That tracks perfectly, and the scientists, they don't just eyeball the color. They measure this change using a spectrophotometer plate reader.
Which is a machine that shoots light through the sample, right?
Yes, it measures the optical density, or OD, at a very specific wavelength of 570 nanometers.
570 nanometers.
Got it. So by comparing the optical density of cells treated with the formulation against untreated control cells, they calculate a critical metric known as the ET50 value.
The toxic exposure time.
Yes. The ET50 calculates the exact exposure time required to reduce tissue viability to 50%.
So if you're developing a regenerative product, you want that ET50 to be really high.
Incredibly high. In fact, if the viability stays near 100% over a 24-hour period, you have a highly biocompatible product.
Oh, wow.
And if that optical density is actually higher than your untreated control, well, you have mathematically proven that your formulation is actively stimulating cell proliferation.
Okay, thinking about this, it's It's a lot like measuring the productivity of a factory.
How so?
Well, if you want to know how well a factory is operating, you don't just stand outside and count the number of workers walking through the door. You measure the electricity output,
Oh, I like that.
right? The MTT assay is measuring the electricity, the metabolic output of the cell, rather than just doing a physical head count.
That is a highly accurate way to look at it. You are measuring the functional machinery. However, I should note, this method isn't without its critics.
Yeah, looking through our sources, I actually have to push back a little on the MTT being the undisputed gold standard.
Go for it.
The literature specifically mentions that because the MTT assay creates those insoluble purple formazon crystals, researchers have to dissolve them using specific solvents.
Right, which requires multiple washing steps in the lab.
Exactly. And doesn't that introduce a fairly massive margin for human error? Like if a lab tech accidentally washes away a few crystals, your viability numbers are artificially skewed downward.
You've hit on a major debate within the biotech community right there. Those washing steps can absolutely lead to false negative or even false positive viability results if the protocol isn't, meticulously standardized.
Right, which is scary if you're evaluating a medical device.
It is. Relying on just one test, especially one with a mechanical washing step, is risky. That's why rigorous laboratories run complementary viability parameters alongside MTT.
I saw the Alamar Blue test mentioned in the sources as an alternative.
Yes, the Rezazurin method, commonly known by the brand name Alamar Blue, it operates on a really similar principle of tracking metabolism.
But no purple crystals.
Right. Instead of creating a solid, insoluble crystal, the healthy cells convert the dye into a highly fluorescent soluble compound called resorphin.
So there's literally no washing required.
None at all. You just measure the fluorescence at a wavelength of 572 nanometers.
Oh, that's smart.
There's also the WST8 kit, which produces a water-soluble dye measured at 450 nanometers. Using these fluorescent and water-soluble tests in tandem with MTT ensures your metabolic data is bulletproof.
Okay, so our polynucleotide formulation has survived the first hurdle. We've proven the cells won't die, and their metabolisms are actually spiking.
Right, a great start.
But here's the reality check. Knowing that cells metabolize happily in a flat, two-dimensional plastic petri dish is cool, but it's not reality.
No, the vaginal canal is definitely not a flat piece of plastic.
Exactly. It is a complex, layered, dynamic ecosystem. So how does a lab actually test this formulation on realistic human anatomy without, jumping straight into human clinical trials?
This brings us to a massive technological leap in the field. To move beyond the flat dish, scientists utilize reconstructed human vaginal epithelium.
RHVE models.
Yes, RHVE models. The sources specifically highlight the epivaginal and skin-ethic models.
So what are we actually looking at with an RHVE model? Is this tissue actually grown from scratch in a lab?
It is. Scientists take immortalized human cell lines like the A431 line, which can divide continuously, and they grow them in a chemically defined medium.
Right.
But the key to making it mimic human anatomy is how they grow it. They don't just submerge the cells in liquid, they culture them at what is called the air-liquid interface.
Wait, so the bottom of the cell layer is sitting in a nutrient-rich liquid, but the top layer is exposed directly to the air.
Exactly. And because the top is exposed to the air, the cells realize they need to protect themselves.
Oh, wow.
Yeah, this forces the cells to stratify. They build protective, distinct layers, exactly how human mucosal tissue naturally layers itself inside the body.
That is
It
fascinating.
really is. Depending on how many days you culture them, these tissues achieve a physiological thickness of between 40 to 270 micrometers.
That's a massive ethical and scientific leap, because historically, products like this were tested using the Drey's rabbit vaginal irritation test, right?
Yes, which was the standard for a long time.
But by growing a 170 micrometer thick layer of actual human cells, we're completely bypassing animal testing while getting vastly superior human-specific data.
It is a profound shift in how we establish biological relevance. But these 3D models aren't just for checking if the tissue gets irritated.
What else do they use them for?
They are crucial for testing a formulation's physical properties. For example, intimate polynucleotides need to have film-forming properties.
Meaning the gel needs to spread out and create a protective physical barrier over the mucosa, like to lock moisture in and keep pathogens out. But how do you test an invisible film on a microscopic 3D piece of tissue?
Through a highly specialized protocol using caffeine.
Wait, like for coffee?
Pure caffeine molecules, yes. Caffeine is used as a chemical probe because it has low lipophilicity.
Meaning it doesn't easily dissolve in fats.
Right. And it has a very well-known, mathematically predictable penetration kinetic across human tissues. Its molecular weight is exactly 194.2.
Okay, let me see if I can put this together. The scientists apply the polynucleotide gel to the top of the 3D vaginal tissue model.
Yep.
Then they drop a specific dose of caffeine on top of that gel. Because they know exactly how fast caffeine normally sinks into unprotected tissue, they just measure the speed now.
You're tracking perfectly.
So if the caffeine easily passes through, the polynucleotide film failed. It didn't protect the tissue. But if the caffeine is blocked, or the absorption is significantly slowed down, the lab has mathematically proven the gel created a physical shield.
You've got it. That is exactly how they prove barrier function. And to take it a step further, they will gently wash the tissue to simulate the natural clearance of vaginal fluids.
Oh, and then run the caffeine probe again.
Exactly. This proves the film's persistency, meaning the shield doesn't just wash away the second the body produces moisture.
So our formulation is doing great. It boosts cell metabolism in a flat dish, and it forms a persistent physical shield over 3D human tissue.
A very successful candidate so far.
But the vaginal tract isn't just layers of epithelial cells, right? It is a highly vascular environment. It's packed with blood vessels.
Highly vascular.
And a protective shield is completely useless if the moment the gel absorbs into the tissue, it sets the underlying vascular network on fire. How do we test vascular safety and severe irritation without risking human subjects?
This requires a shift to one of the most, visually striking biocompatibility parameters in the literature. It's an assay known universally as the HET-CAM assay.
HET-CAM.
Yes, which stands for the hen's egg test choriolentoic membrane.
The unhatched egg test. I teased this in the intro. This is so fascinating to me. Walk us through the mechanics of this.
The HET-CAM is an ingenious in vitro alternative to animal testing. You take a fertilized hen's egg and incubate it for precisely 9 days.
Okay, 9 days.
On day 9, the embryo is developing, but it hasn't actually formed pain receptors yet. You carefully open the shell to expose the choriolentoic membrane.
Which is essentially just a dense, living web of tiny blood vessels.
Yes, it is a highly vascularized membrane that perfectly mimics the sensitivity of human mucosal blood vessels.
Wow.
In the lab, researchers apply the polynucleotide gel directly onto these living blood vessels. And from the moment of contact, a clock starts.
What are they doing while the clock is ticking?
They observe the vessels under magnification at highly specific intervals, usually 30 seconds, 2 minutes, and 5 minutes.
And what kind of vascular damage are they looking for?
They track 3 specific parameters. First, hemorrhage are the blood vessels bleeding into the surrounding tissue.
Okay, bleeding is bad.
Second, lysis are the vessel walls actually dissolving and disintegrating.
Yikes.
And third, coagulation are the intra- and extravascular proteins denaturing.
When you say protein denaturation in the blood, you mean the proteins are unfolding and clumping together, right? Kind of like an egg white turning solid when it hits a hot pan, but happening inside the living blood vessel.
That is an excellent way to visualize coagulation, yes. And obviously, it disrupts the entire blood flow.
Right.
Based on the time it takes for any of these 3 reactions, hemorrhage, lysis, or coagulation to occur, the formulation is assigned an irritation score, or IS. The scale goes from 0 up to 21.
And for a medical device like an intimate polynucleotide to pass, what score does it actually need?
The crucial laboratory parameter to be classified as a non-irritant is an irritation score between 0 and 4.9.
That's a pretty tight window.
It is. Anything above 4.9, and the product is deemed too harsh for intimate mucosal application.
Using a developing egg's blood vessels as a stand-in for human mucosa is incredibly clever. You get dynamic, living vascular reactions that a flat petri dish could never give you.
Right, and you completely avoid traditional animal testing.
But let's say the formulation gets a 0 on the egg test. No bleeding, no coagulation. Is it officially biocompatible at that point?
Not quite. The HET-CAM assay is fantastic for ruling out severe, immediate vascular irritation, but true biocompatibility also requires looking at invisible molecular inflammation. Even if the blood vessels don't burst, the local immune cells might be in a state of quiet panic.
So we need a test for quiet immune panic. If I'm thinking about the immune system's first responders, we're talking about macrophages, right?
Precisely. Macrophages constantly patrol the tissue. If they detect something foreign and irritating, even if it doesn't cause visible bleeding, they start releasing inflammatory chemical signals.
To call in reinforcements.
Exactly.
So the lab exposes cultured macrophages to the polynucleotides and measures those signals.
Yes. One of the primary parameters labs measure is nitrite concentration, which serves as a stable indicator of nitric oxide, or NO, production.
How did you see that?
They use a fluorometric approach, adding a reagent that literally glows when it reacts with nitrate.
Okay, so if it glows brightly, that's bad.
Right. If the nitrite levels in the fluid remain low, comparable to a negative control where nothing was added, it proves the formulation isn't triggering a deep molecular inflammatory response.
It really is a gauntlet.
Mhm.
It has to pass the MTT metabolic test, the 3D RHVE barrier test, the HET-CAM vascular test, and the macrophage nitrite test.
And that just covers the biology.
Right, because a biostimulator still has to survive the physics of the human body. Once safe,
The mechanical and chemical environment of the vaginal tract is incredibly demanding. This is where laboratory texture analyzers come into play to test a parameter called bioadhesion.
bioadhesion.
For this, scientists typically use ex vivo porcine or pig vaginal tissues.
And they use pig tissue because the histological structure of the mucosa is very comparable to human tissue
Right.
in terms of density and elasticity.
Yes, it provides an excellent mechanical proxy. In the lab, they clamp the porcine tissue into a testing machine.
Okay.
They apply the polynucleotide gel to the tissue, and then a mechanical probe attaches to the gel and physically pulls it away. The machine measures the tensile force or work of adhesion.
Measured in gram millimeters, according to the sources.
Correct. It calculates the exact kinetic energy required to break the bond between the gel and the mucosa.
Wow.
But to make it realistic, they don't do this on dry tissue. They introduce a laboratory substance called vaginal fluid simulant, or VFS.
Which makes sense, because the human body is constantly producing fluids to clear out cellular debris and foreign matter. It's kind of like testing Velcro in a rainstorm.
That's a very fitting analogy.
The VFS is the rain trying to wash everything away. If the biostimulator doesn't have the right tensile force, if the Velcro isn't strong enough, the active DNA fragments just slide out of the tissue before they ever have a chance to stimulate the fibroblasts.
The formulation must prove mathematically that it can handle human vaginal fluid clearance to prevent premature leakage.
Makes total sense.
And speaking of the chemical realities of those fluids, the lab also has to test pH.
The healthy vaginal pH is strictly acidic, usually between 4.0 and 4.5. And that acidity is the primary defense mechanism against bacterial vaginosis and other pathogens.
Yes, that acidic environment is crucial for keeping saprophytic lactobacilli, the good bacteria, thriving. So a regenerative product cannot disrupt that balance.
Right.
The lab measures a parameter called absolute buffering capacity, or ABC.
So if the healthy pH is acidic, I imagine the lab has to bombard the formulation with an alkaline substance, like to see how long it takes to break its acidic defense, kind of like a stress test for the microbiome.
You're exactly on the right track. They take the formulation and slowly titrate in sodium hydroxide, which is a strong base.
Okay.
The absolute buffering capacity is the exact amount of sodium hydroxide required to raise the pH of the formulation by 1 single unit.
So this proves how strongly the gel will fight to maintain its acidic environment once it's inside the body.
Exactly. Even when it is exposed to highly alkaline fluids like semen or menstrual blood.
It has to be incredibly stubborn about staying acidic. But this brings up a massive contradiction for me.
Oh, what's that?
We talked earlier about the MTT assay and making sure the ET50 viability score stays high, meaning the cells aren't dying. But acids inherently burn cells. If a formulation is highly acidic to protect the microbiome, doesn't that acidity inherently irritate the delicate mucosal cells and drop your viability scores? How do bioengineers balance being acidic enough to stop bacteria and gentle enough to pass the MTT and the egg tests?
That is the ultimate formulation tightrope, and it is the exact reason you rarely see polynucleotides formulated in isolation for intimate health.
They need help.
Yes. The bioengineers have to carefully balance the raw DNA fragments with specific excipients that buffer the environment. For instance, lactic acid is frequently used.
Why lactic acid specifically?
Because it provides that physiological acidity natively without the tissue-destroying harshness of a synthetic acid.
And I noticed in the protocols they often include glycerin.
Yes, glycerin is added to soften the chemical impact. It maintains deep tissue hydration and acts as a humectant.
So it's protecting the cell membranes while the lactic acid holds the pH line.
Exactly. It's a completely synchronized system.
The lactic acid acts as the bouncer, keeping the alkaline pathogens out. The glycerin keeps the cellular environment comfortable and hydrated. And the polynucleotide fragments sneak in behind that shield to signal the fibroblasts to rebuild the tissue.
And every single one of those interactions, The acidity, the hydration, the cellular signaling is quantified by the exact laboratory parameters we've discussed today. Nothing is left to assumption.
When you look at all of this together, it really shifts how you view these products. The real takeaway here for you listening is that intimate wellness is undergoing an engineering renaissance.
It truly is.
When you hear about non-hormonal regenerative treatments like intimate polynucleotides, you now know that the phrase safety and efficacy isn't just generic marketing copy.
Not at all.
It is a status forged in fire. It is backed by a punishing gauntlet of precise laboratory parameters. From the 570-nanometer optical density readings to track cell metabolism, to the vascular observation in the 9-day egg test, to the mechanical tensile force pulling gel off porcine tissues, we are moving from generic, intimate moisturizers to rigorously engineered biotherapeutics.
The level of detail and foresight required to bring a biological product from a raw DNA fragment to a clinical setting is just staggering. The testing models have evolved to match the sheer complexity of the human body.
And looking at where this evolution is heading, I want to leave you with a thought to mull over. If we're already growing 3D tissue models at an air-liquid interface to test these gels, it's not a huge leap to imagine a future where personalized medicine takes this even further.
Oh, absolutely.
Could we soon reach a point where your own cloned mucosal cells are cultured in the lab? Imagine a scenario where a custom MTT or RHVE assay is run using your unique DNA and your specific cellular metabolism.
That would be incredible.
Right. We could predict exactly how your body will react to a specific regenerative treatment before you ever step foot in a clinic.
That would be the ultimate end to the diagnostic muddy waters, just completely tailoring the laboratory gauntlet to the individual patient.
A fascinating possibility to keep an eye on. Until next time, keep diving deep.